Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. Today we will discuss draw-off nozzle hydraulics and nozzle cavitation due to lack of hydrostatic head. I imagine that many viewers might skip this video. After all, a nozzle is simply a hole in a vessel, flanged up to a pipe as shown in picture. Why a whole video? Well, it is not that simple. Lots of process problems occur due to improperly designed draw-off nozzles. Nozzle exit loss. The pressure drop of a fluid flowing through a nozzle is equal to delta H equals 0.34 times V2, where delta H equals pressure loss of the fluid as it flows through the nozzle, in inches of fluid, V equals velocity of the fluid as it flows through the nozzle, in feet per second. This equation assumes that before the fluid enters the nozzle, its velocity is small, compared to its velocity in the nozzle. The increase in the velocity, or the kinetic energy, of the fluid in the nozzle comes from the pressure of the fluid. This is Bernoulli's equation in action. The energy to accelerate the fluid in the draw-off nozzle comes from the potential energy of the fluid. This is Newton's second law of motion. The coefficient used in the equation above, 0.34, assumes the process fluid has a low viscosity. For most process nozzles, this is a reasonable assumption. Detailed information on draw-off nozzle coefficients has been published in Crane, Flow of Fluids Through Valves, Fittings, and Pipe, technical paper. For me, I don't trust published coefficients. I like to prove it myself, prove it by experimentation. What I'm doing is running water into the bathtub at a measured rate. I wait for the water to drain out until an equilibrium height is established. I have to get the height, dH, high enough to suppress vortexing. Then, using the diameter of the drain, I calculate the velocity, v, of the water flowing out the drain. I can then calculate the coefficient, 0.34. Let's take a close look at the use of the term delta H. This picture shows a bucket with a hole punched in its side. The velocity of the water as it escapes from the hole is v in the preceding equation. The height of water in the bucket above the center of the hole is delta H. If we replace the water in the bucket with gasoline, which has a lower density, the same hole velocity would occur with the same height of fluid. The pressure drop of the fluid escaping from the bucket is called nozzle exit loss. Actually, nothing is lost. The potential energy, or pressure head of the water in the bucket, is just converted into velocity or kinetic energy. Converting delta H to pressure drop. A column of water 28-inch high exerts a head pressure of 1 psi, as shown in picture. To determine the pressure drop of water flowing through a hole, in pounds per square inch, we would calculate delta P equals 0.34 divided by 28-inch times V square, where delta P equals pressure drop in psi. But perhaps we have gasoline flowing through the hole. The density of water is 62 pounds per cubic feet, the density of gasoline is 40 pounds per feet cube. Since the weight, or pressure head, of a column of fluid is proportional to its density, we calculate delta P equals 0.34 divided by 28-inch times 40 divided by 62 times V square. Again, delta P is the pressure drop, in psi, of the gasoline escaping through a hole in the bucket. If we have a vapor flowing out of the overhead nozzle on a fractionator, as shown in picture, the pressure drop of the vapor escaping from the vessel in the overhead vapor line is delta P equals 0.34 divided by 28-inch times dV divided by 62 times V square, where delta P equals pressure drop of a fluid, psi, dV equals density of a fluid such as a vapor in pound per feet cube, and V equals velocity of fluid in nozzle in feet per second. This is an important equation to remember. It is the pressure drop through a hole equation. It works for water, steam, air, gasoline, alcohol, and all other fluids, unless viscosity is important. A viscosity of less than 5 or 10 centipoise, CP, or centistokes, CST, such as hot maple syrup, means that viscosity is not important. Critical flow. Everything I have just said is wrong when the fluid we are working with undergoes critical flow. First, critical flow applies only to compressible fluids such as vapor, steam, air, or gases. Second, as long as the pressure drop that we calculate through the nozzle is less than 20 or 30% of the upstream pressure, we can ignore critical flow. Critical flow occurs when a compressible fluid velocity approaches the speed of sound, about 1,000 feet per second. Process piping handling vapor is typically designed to work at a velocity of 100 feet per second. Nozzle limitations. This picture is an exact representation of my bathtub. When my tub has a water level of 28 inch, the pressure right above the drain, at P1, is 1 psi. Having bathed, I now pull the plug. I also start the water running into the tub, to keep the water level at 28 inches. The velocity of water flowing from the tub through the drain is 20 feet per second. The pressure drop, in psi, of the water as it escapes from the tub, is delta P equals 0.34 divided by 28 inch times 20 square equals 5 psi. The pressure at P1 is now the 1 psi static head minus the 5 psi nozzle exit loss or negative 4 psig, or positive 10.7 psia. That is, the pressure at the drain is a substantial partial vacuum, or a negative pressure. By the term negative pressure, I mean that it is below atmospheric pressure. Atmospheric pressure at sea level is 16.7 psia. This suggests that the pressure in a water drain can get so low that air could be sucked out of the bathroom and down the drain. Of course, we all see this happen several times a day, typically when we flush a toilet. So much air is drawn into the water drainage piping that we install vents on our roofs to release this air. The only requirement, then, for vapors to be drawn into a flowing nozzle is for the nozzle exit loss to be larger than the static head of liquid above the nozzle. Incidentally, if a bird builds its nest on top of one of our roof toilet vents, we find the toilet will no longer flush properly. The experienced plumber states that the toilet won't flush because it is suffering from vapor lock, and this is true. A working knowledge of process equipment fundamentals often comes in quite handy around the home. Effect of bubble point liquid. We sometimes bath in boiling water. Draining a vessel full of liquid at its bubble or boiling point prevents the formation of a negative pressure, or partial vacuum, in the drain. As soon as the vacuum begins to form, the liquid will begin to generate vapor. This vapor would tend to restrict the flow of liquid as it exits the drain, and thus reduce its flow rate. As the velocity of the liquid flowing into the drain decreases, the pressure of the liquid at the inlet to the drain will increase. This increase in pressure will be just sufficient to suppress vaporization of the liquid in the drain, that is, the liquid velocity will be reduced just enough to cause sufficient increase in pressure to prevent the liquid boiling. This picture illustrates the side draw-off of a fractionator. The liquid at point A is at its bubble or boiling point. We can be quite sure that this is true, because the liquid and vapor are in intimate contact at the vapor-liquid interface. We say that the vapor is at its dew point, and that the liquid is at its bubble point. But how about the liquid at point B? Is this liquid also at its boiling or bubble point? It is the same liquid, having the same temperature and composition as the liquid at point A. But the pressure at point B is slightly higher than the pressure at point A. The pressure at point A is the pressure in the vessel, 10 psig. The pressure at point B is the pressure at point A plus the static head of liquid H, shown in picture. Let's assume that this liquid is water. Also, H equals 28 inches. Then the pressure at point B is 10 psig plus 28 inch divided by 28 inch H2O divided by psig equals 11 psig. The boiling point of water at 10 psig is about 240 degrees Fahrenheit. This means that the temperature in the entire water draw-off sump is 240 degrees Fahrenheit. But the pressure at point B is 1 psi above the water's bubble or boiling point. We say, then, that the water at point B is subcooled by an equivalent of 28 inch of liquid, or 1 psi. But how about the pressure at point D? The liquid at both points B and D has the following in common. Same elevation. Same fluid temperature. Same fluid composition. If liquid is flowing through the nozzle, as shown in picture at, say, 9 feet per second, the pressure at point D will be lower than that at point B. Assuming the velocity in the draw-off sump to be close to zero, we can calculate the pressure at point D as follows. Head loss due to increased velocity is equal to 0.34 times 92 equals 28 inch of water. As 28 inch of water equals 1 psi of head pressure, the head loss due to increased velocity at the nozzle exit equals 1 psi. Thus, the pressure at point D will then be 11 psi G minus 1 psi, that is, 10 psi G. Cavitation. For practice, calculate the pressure at point D assuming that the nozzle exit velocity is 10 feet per second. If you calculated 9.8 psig, you are likely wrong. You see, the water will start to flash to steam if it falls below its boiling point pressure. The boiling point pressure of water at 240 degrees Fahrenheit is 10 psig. As steam is evolved at a lower pressure, the large volume of vapor chokes off the flow in the draw-off nozzle. The flow of water slows down. As the velocity of the water decreases, its pressure increases. The pressure will increase to 10 psig, that is, the boiling point pressure of water at 240 degrees Fahrenheit. At this pressure, the vaporization of the liquid in the draw-off nozzle is zero. In summary, the lowest pressure that can be reached at point D in picture. 16.6 is the pressure at point A. When these two pressures are equal, we say that the draw-off nozzle is limited by cavitation. If we were to lower the pressure downstream of point D, say, by opening a control valve, the increase in flow would be zero. Vortex breakers in draw-off nozzles. The coefficient for nozzle exit loss of 0.34, shown before, assumes that there is no vortex breaker in the nozzle. Vortex breakers are certainly required if nozzle exit velocities exceed 4 feet per second. Vortex breakers are usually not needed if velocities in the draw-off nozzle are less than 2 feet per second. As most such nozzles are designed at less than 2 feet per second, in general vortex breakers are not needed in most applications. However, many process plants have vortex breakers in all draw-off nozzles as part of their standard spec. This is bad for two reasons. Vortex breakers create turbulence, reduce the open area of nozzles, and thus lead to premature nozzle cavitation limits. Much more importantly, vortex breakers trap rags, gloves, and other trash left in towers during construction or turnarounds. If a draw-off nozzle is equipped with both a down-comber seal pan and a draw-off box, then the draw-off nozzle is difficult, and oftentimes impossible, to inspect. Installing a vortex breaker that is not needed due to low draw-off velocities is just looking for trouble, without any justification. If you note a trace of bitterness pertaining to the overzealous use of vortex breakers, it is not without reason. The use of a totally unneeded vortex breaker in the bottom of a 90,000 BSD vacuum tower in one refinery cost the new owners of the plant many millions of dollars in lost gas oil production. If you must use a vortex breaker, please consult Norman P. Lieberman book, Process Design for Reliable Operations, to see how one can design a draw-off sump to prevent the vortex breaker from fouling. External restrictions. This picture shows two almost identical draw-off arrangements. The only difference is the elevation of the control valve in the draw-off line. Control valve A is at the same elevation as the draw-off nozzle. The pressure drop across the control valve is 2 psi, or 56 inch of water. Let's assume that the increase in velocity through the draw-off nozzle is small, and hence the nozzle exit loss is zero. The frictional loss through the piping and nozzle is zero. Even after we have made these two unlikely assumptions, the height of hot water in the draw-off sump must still be 56 inch above the center line of the draw-off nozzle. If not, the water would begin flashing to steam as it experienced a pressure drop of 2 psi flowing across the control valve. The evolved steam would then choke the water flow, reducing the pressure drop across the control valve until the pressure drop equaled the depth, or head, of water in the draw-off sump. Control valve B in picture is located 56 inches below the draw-off nozzle. The pressure drop across the valve is still 2 psi, or 56 inch of water. Again, we will neglect nozzle exit loss and friction loss. But in this case, the height of water in the draw-off sump may be 0. Why? Referring to picture, the pressure head of water above control valve B is an extra 2 psi, or 56 inches of water. Thus, even if control valve B loses 2 psi of pressure, the water will not flash to steam. And this is true even when the sump is almost empty. Does this mean that control valves should be located well below the elevation of the draw-off nozzle? Yes. Does this mean that the amount of piping, fittings, gate valves, etc., should be minimized on a draw-off line until the line drops 10 or 20 feet below the draw-off nozzle? Yes. Does this mean any frictional losses due to external piping at the same elevation as the draw-off nozzle have to be added to the nozzle exit loss in determining the liquid level in the sump? Yes. Increasing flow from a draw-off sump. If the flow is limited by nozzle exit loss, because the nozzle diameter is small or because the sump is shallow, no process change will increase the flow. However, if the restriction is outside of the vessel because of valves, fittings, or piping on the draw-off line, located at the same elevation as the draw-off nozzle, then there is an option to marginally increase flow. Remove the insulation on the piping immediately downstream of the nozzle and spray cold water on the bare pipe. Reducing the temperature by a few degrees will subcool the liquid and suppress inline vaporization or cavitation. This should permit an increase in the flow of product. It's the same idea as the common practice of operators spraying water on the suction of a hot pump to suppress pump cavitation as the flow rate is increased. Overcoming nozzle exit loss limits. An engineer once tried to increase the flow of jet fuel from a crude distillation column by opening the draw-off flow control valve. Opening the valve from 30 to 100% did not increase the flow of jet fuel at all. This is a sure sign of nozzle exit loss or cavitation limits. To prove point, he increased the level of liquid in the draw-off sump from 2 to 4 feet. Since flow is proportional to velocity and head loss is proportional to velocity square, the flow of jet fuel increased from 1000 to 1414 GPM. That is, the flow increased in proportion to the square root of the increase of liquid level in the sump. But the sump was only 4 feet high, and he needed to increase jet fuel flow even further. So, he raised the pressure in the crude column from 10 to 14 psi. This increased the pressure in the draw-off sump by 4 psi. The results of this increase in pressure are shown in picture. At first, the increase in pressure greatly increased the flow of jet fuel. But after a few minutes, jet fuel flow slipped back to its original rate. What happened? The problem is equilibrium. When the pressure in the tower was raised, lighter components from the vapor were forced to dissolve in the pool of liquid in the draw-off sump. This meant that, at the new equilibrium conditions, the lighter liquid would boil not at 10 psi but at 14 psi. But the composition of the liquid already in the sump did not change for a while. It took some time for the lighter liquid formed at the vapor-liquid interface to displace the heavier liquid already in the sump. During this period of time, jet fuel flow increased. But when the lighter liquid reached the draw-off nozzle, it began to vaporize. Flow was choked off by the evolving vapors, until the flow was reduced to the original rate. This is another symptom of a tower draw-off limited by nozzle exit loss or nozzle cavitation. The rule of errors. This incident about the jet fuel draw-off happened at the Chevron Refinery in 1987. The concept of the surface of a liquid pool reaching equilibrium with an altered vapor phase before the bulk of the liquid reaches equilibrium is a really useful idea. It's one of the reasons for a lag between a step change in an independent variable and the response of a dependent variable. This incident got an engineer thinking about the interrelationship between process dynamics and vapor-liquid equilibrium. So, even though engineer had made an error, he gained some important insights. Most of the things you can learn are through field observation. Sitting in the office, you're warm and safe. Safe from making errors. But to progress, to learn, to advance the process and yourself, you've got to take chances. The chances are that if you go out to the plant and try a new idea, it will work. 90% of the time you will be wrong. But 100% of the time you'll learn something new. Nozzle exit loss calculation. My standard calculation for nozzle exit loss as shown at the start of this video is delta H equals 0.34 V square, where V equals velocity in feet per second, delta H equals head converted to velocity, in inches, measured from the center of the nozzle. The coefficient of 0.34 is one that I've arrived at by measurement in my water barrel and bathtub, and then added a small safety factor for design purposes. The actual theoretical calculation for converting head to acceleration. Step 1, let's assume that I have 1 pound of liquid flowing through a nozzle at a velocity of V feet per second. Step 2, to increase the kinetic energy of the liquid from no velocity to V requires 0.5 m V square, or since m equals 1 pound of mass we can say 0.5 V square. Step 3, I'll now divide by the gravitational constant at the surface of planet Earth, 32.2 feet per second squared. 0.5 feet second square divided by 32 feet per second square, or 0.0155 V square feet. Step 4, to convert feet to inches of liquid, I'll multiply by 12. 0.0156 V square feet times 12 inch per feet, or 0.19 V square inches. Then delta H in inches of liquid equals delta H equals 0.19 V square. The difference between the 0.19 coefficient in equation and the 0.34 coefficient in equation is due to friction losses through the nozzle and my safety factor used for design. All I have done with the above calculation is convert kinetic energy into potential energy. The purpose of this calculation is to demonstrate that there is a real theoretical basis for some of my basic rules of thumb. One of the best ways to improve one's engineering skills is to compare, on a quantitative basis, engineering theory and practice. Pressure recovery in nozzles. If pressure is partially converted to velocity as a fluid accelerates through a nozzle, does this suggest that as a fluid enters a vessel through a nozzle, its velocity is partly converted back into pressure? Actually, I have observed this small effect in vacuum tower flash zone inlets, when I was measuring pressures to the nearest mm of Hg. Perhaps 1/2 to 1/3 of the energy used to accelerate a flow as a fluid enters a pipe from a vessel might be recovered when the fluid exits the pipe into a downstream vessel. The pressure not recovered is due to friction and turbulence. I almost always ignore nozzle pressure recovery in my calculations in field troubleshooting except in vacuum tower applications. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.